Hi, everyone, and welcome to today's event, How the Federal Government Can Increase Access to Supercomputing Across America. My name is Hodan Omar, and I'm a policy analyst at the Center for Data Innovation, a non-profit, non-partisan think tank focusing on the intersection of data and public policy. Before we begin, a couple of logistical points. You can join the conversation by posting questions in Slido using the hashtag supercomputing, or feel free to tweet using our handle and the hashtag data innovation. All right, so the question we want to explore in today's event is what steps do policymakers need to take to increase access to supercomputing resources across the nation for AI researchers who need it? This is a really important conversation because the ability for AI researchers to use and exploit HPC in solving problems of economic, national security, and societal importance will determine in part the future of the United States. So we released a paper this week that's really looked at how much funding there currently is for supercomputing resources, where the need for access is greatest, and how access differs across different demographic groups. And to discuss the findings of this report, we have a really fantastic panel with us today. We have Andrew Jones, who's planning future HPC and AI capabilities at Microsoft, Cheryl Martin, who is the Director of Global Business Development, Higher Education and Research at NVIDIA, and Sharon Brody-Geber, who is the Director of the Women in HPC Organization's Chapters and Affiliates Program, as well as the Director of Advanced Research Computing at the University of Michigan. But before we jump into a conversation with the panel, I'd like to spend some time giving an overview from the report. For those joining at home, you can find a copy of the report on our website and a link to it on our event page. Great. So, a good place to start in this conversation, I think, is to get on the same page about what we mean when we say high-performance computing and supercomputing. HPC systems are those that have the computational power to solve difficult computational problems. Supercomputers are a subset of HPC systems and describe any computer that is one of the largest, fastest, and most powerful available at any given time. So, for example, the fastest HPC system in the world right now is Fugaku, a Japanese supercomputer like the one shown here. But these systems can't solve problems efficiently if they don't have the right software to exploit their capabilities, or there aren't people with the skills to use them, which is why high-performance computing in general should be understood as a culmination of hardware, software, and expertise. And in this conversation about increasing access to HPC, we need to remember that means increasing access to all three of these components. So at a high level, the report really identifies three problems in increasing access to supercomputing in the United States. The first is that there isn't enough funding in HPC to support the acquisition of systems and software that can support AI researchers. The second is that there is geographic disparity in access to HPC. For example, some states have institutions with really great computer science programs and are conducting more AI research than other states, and yet they have less access to HPC systems than others. And finally, some groups are underrepresented in HPC, namely women and minorities, which isn't only unfair, it really hurts US competitiveness. So looking first at the amount of funding. Funding in HPC in the United States predominantly flows through the Department of Energy and the National Science Foundation. DOE in general invests in kind of the most powerful systems like the Summit supercomputer at Oak Ridge, that is the second most powerful in the world, but it supports a small number of researchers. Whereas NSF is primarily responsible for center-class systems, which we define in the report as those that aren't quite as powerful, but they support the majority of researchers, which means that they support a significant proportion of research advances. And so what the graph you're seeing now shows in the light salmon color is that NSF investments in HPC have fallen, approximately 50% when we adjust for inflation. And if we focus on just NSF for a moment, we can also see that over the same time period, demand for access to NSF's systems has increased dramatically. Demand here is measured in service units, which are essentially just units of compute time. But what we can see is that by the time we get to 2019, the HPC resources that NSF is making available through its funding, which is shown in the red line at the bottom, is supporting only about a third of demand, which is shown at the top in orange. And we actually see the same thing for DOE. So if we go back one slide, even though their funding has been growing, it's not been growing enough. It's increased over the last 10 years by about 90% when you adjust for inflation, but it's still only supporting about a third of demand. So this gap that we're seeing is increasing for DOE too. And it's only likely to keep growing unless something is done. And our reasoning for what should be done in the report is simple. If current funding, which we saw to be about 700 million in total for both DOE and NSF in the previous slide, is supporting systems that can cater for a third of demand, Congress will need to authorize NSF and DOE spending to at least triple. Tripling spending per year would bring us to a little over 2 billion in HPC per year, which over 5 years would bring us to about 10 billion in funding. And since this is a question of competitiveness, it's worth noting that the EU announced just a few months ago that it will increase its own spending to 8 billion euros, which is about $9.6 billion. So if any policymakers are balking at a number like 10 billion, they only need to look at the EU or even China or Japan and see how much they're spending as a percentage of their GDPs. Okay, so we've said that the federal government should provide 10 billion in funding to support more access to HPC systems. But which states should the government invest in, and which institutions should it partner with? That's what brings us to our second problem. Some states already have more access to HPC than others, and even within those that don't have access, some are doing more AI research than others. To figure out where HPC is needed the most, policymakers should first measure how states are currently using HPC resources for AI research. This is what we do in the report. We first look at where states already have access to compute time from NSF, which is shown in the graph as shading in orange. The more orange a state is, the more access to HPC compute time from NSF that state has. At the same time, we look at how much funding the state has in computer science. The bigger the circle, the more funding. The states we're going to be interested in are the ones with lighter shading and bigger circles, because those are the states which lack access to HPC, but have significant research programs in computer science. So if we extract those states, then we'll get a map of the states that need HPC resources for AI the most. These are the states that NSF should be investing in. States like Alabama, Indiana, Utah, Georgia, Florida, Texas, and Hawaii. But the thing is, even if we get the funding right, the funding amount right, and the funding locations right, there is still another big obstacle to overcome in increasing access to HPC, and that's the who. The final problem is that some groups are underrepresented in HPC, which means that not all individuals have equal opportunity to succeed in becoming the next generation of AI researchers. So for example, women only make up 17% of the HPC workforce. This is partly because there's a gender imbalance in people with science and engineering backgrounds that ultimately make up the HPC community. In addition, there's a lack of participation from Black, Hispanic, and Indigenous people in HPC. A significant portion of these researchers are at minority-serving institutions, and yet these institutions lack access to resources. To address this, the report calls for NSF and DOE to better support partnerships that coordinate the sharing of computing resources with minority-serving institutions, or MSIs, which include historically Black colleges and universities, Hispanic-serving institutions, and tribal colleges and universities, as well as re-establishing targeted grants that fund HPC resources at MSIs. In addition, to support the pipeline of qualified women candidates in HPC, NSF and DOE will need to encourage more women to enroll and persist in engineering and science-based computing degree programs by providing funding initiatives across the country that improve recruitment and retention rate of women in computing majors. So for example, NSF has provided funds to the Mississippi Alliance for Women in Computing to do just this, which is great, but we need more of this across the country. So that gives a high-level overview of the report, but to get more details about it or to read about the other recommendations we call for, you can find a full copy on our website. And I will end there and bring on our panelists. Hi, thanks all for joining us. Cheryl, I wanted to start with you. Florida is one of the states that I mentioned in the report as one that NSF should direct its funding toward. And NVIDIA is changing this by recently partnering with the University of Florida. How is the University of Florida making use of this system? And what is your take on who should be responsible for providing access to computing infrastructure? And what level of compute should they be providing?
And thanks for the question. It's actually quite a lot of things to answer, but I think I'll start with the back part of it first, which is, who should be responsible for providing this? And I think the simple answer is it's all three. It's got to be a combination of, we've got to do a better job of doing public-private partnerships. And on the public side of it, it's got to be not only federal government, but I also think state government. And we really believe that what we've done at University of Florida is a really good example. We hope for it to be a framework of how other universities and how other places across the United States can do something similar. And again, in that case, the partnership is not just for research only, but it's a combination of research and a combination of skills and curriculum. And then also a good portion of this is the sort of redevelopment or the increase in skills and capabilities from the faculty. So it's a pretty big change for a good portion of the faculty as they look at this extending throughout the entire university. So this actually started several years ago, and Chris Malachowski, who is a University of Florida alumni, and he's also an NVIDIA co-founder, was spending a lot of time with their engineering groups and other groups, and he started challenging them that they needed to think a lot bigger. They tended to put their, as they thought about research, they tried to fit into their current capabilities and what it is that they were able to even do within their own university. And he just really pushed them. You've got to think more cross-discipline. You've got to think bigger. And that's where they started thinking, and they started looking at more grand challenge type of things that they would be able to do if they started thinking bigger. And that's really where this, it was a donation from Chris. And instead of giving money, he said, I want to do something that's really going to change it. And so by being able to donate the compute power. So they're just now, literally, as we talk, they're in the process of installing the systems. It should be up and available to all the users at the beginning of January, but they really started this transition early this year. And so spending a lot of time on curriculum, on training of, again, both students and faculty. And this week they announced $1 million worth of funding, basically seed funding. And so what they asked was for the faculty to go back and take a look at, where are some of those cross-discipline kinds of research that you would like to be able to do. And so they gave out 20 awards for $50,000 each. And they ended up with 133 proposals, of which they were able to fund 20 of those. So there's obviously a lot of opportunities and some really great things that are going on there. And they kind of spanned everything from early detection of Alzheimer's, which, more typical research, to, things around student engagement and being able to identify, even in remote learning, being able to identify at-risk students. So some great opportunities to, for uses of AI across the university. So we're also in some early stages of engaging with with some other industrial partners, particularly on the healthcare side. So we did a similar project in the UK called Cambridge One, where we're working with a lot of the pharmaceutical companies and with the universities in the UK. So we're looking to do something similar at Florida as well. So I think it's a great framework that can be leveraged in other places. And when you ask how much we should be investing, I think you've got to take into consideration, you did a great job of showing that we're, maybe a third of the way there to meeting what the current demands are. The thing that we've got to keep in mind is that the current demands are just the very tip of the iceberg. As this starts to expand to every discipline in a university, every industry that's out there, every discipline then needs to start to participate. The growth curve of this is going to be enormous. And so, I think we're really way underrepresented today, as you pointed out, but I think the growth curve is even higher.
Thanks. Andrew, what are your kind of initial thoughts on this and the difference between kind of institutional responsibility?
I think that's a good point that Gerald drew out at the end there. It's not so much the fact that there's a difference between supply and demand, because there will always be way more demand for computing resources than we can ever hope to supply with any reasonable amount of funding. But the fact that those curves are diverging is the worrying concern. The fact that the demand is growing so much faster than the supply of resource, that essentially is saying we're artificially increasing the constraints on the science. We're locking the science down to constraints. So that to me is the challenge, is the divergence of those two curves. It does require contributions, investments, and effort, and it's not just the funding; it's the time and the effort and the institutional commitment from both institutional, local levels, national levels, and then from the private sector as well. And I think it's all of those things need to come together, because otherwise you're going to end up with a friction somewhere that just slows the whole thing down. And as you said in the introduction, that needs to cover the people side, the expertise side, the software side, the operational costs, and the infrastructure costs, and so on. It needs to be a full spectrum response. Otherwise, you're just going to stick a computer in a room and not a lot of science is going to come out of it.
You've actually written and spoken a lot about the total cost of operating an HPC system. and federal rules differentiate between what's considered a direct and indirect cost for different types of HPC systems. Can you talk a little bit about how those costs differ and what impact that has on institutions as they decide on how they're going to invest and whether they're investing on-site or cloud computing?
Yeah, sure. So for the last point, whether it's on-prem or cloud to a certain extent is very much a second or third order effect at this point. It's access to the capability overall. On-prem versus cloud is just a means of delivering that. The real thing is to make sure that the researchers have the freedom to pick the best technology to unlock the science they want to do, and then to deliver the best impact to their science programs, to society, to the economy, to whatever. And that means, again, in other terms, we have the constraint of capacity. We need to make sure we're not constraining people by putting artificial labels on money to constrain how it's being spent. So, for example, CapEx versus OpEx, capital costs versus operating costs, or direct funding versus indirect funding or overheads, or equipment budgets versus people budgets. Putting arbitrary boundaries and limitations on this is constraining the researchers from being able to pick the best solution for their needs, and it will be different. One university, one particular mix of science groups, one particular mix of researchers in a different university, they will have different needs to tune those different parts of funding to deliver the best value overall. And it does need to look at the total cost of ownership or the total cost of solution, which is not just the hardware, not just the software, not just the people, the operating costs, the data center costs, things like business continuity and planning and technology evaluation and investing in future algorithms, as well as just the current state of the codes and so on. So there's a bigger picture that needs to be taken into account with this whole total cost of ownership, but also, as I said, the labels on the money, and ultimately give the researchers the freedom to unlock what they need to do the science.
Thanks. Sharon, you recently co-authored your own kind of comprehensive survey of cloud and on-prem HPC usage at academic institutions. And one thing that kind of jumps out from the paper is that institutions continue to evaluate cloud solutions, even though they've concluded them to be more expensive. Can you expand on what the survey found and what that means?
So I'd like to, before that, I'm going to put in my own personal opinion that I've stated before. We all use something called the Branscombe pyramid, which you, of course, mentioned in your report. It's from 1993. At the time, it was seen as there was an on-ramp going from small campus resources all the way up to leadership. My opinion is that we need to start looking at the pyramid not as an on-ramp, but seeing it as a toolkit. There's still different amounts of resources needed in each of the categories. And right now I would put commercial cloud resources at the very tip. But it isn't that you go up from one level to the next necessarily. Some people do. They start small. They need to then go all the way up to larger resources. But many times it's what is the tool you need. This is exactly what Andrew said. What is the tool that you need to get a certain thing done? So we continue at institutions to look at commercial cloud because there are needs that cannot be met because of financial reasons, capacity or capability at an institution. So we need to think of commercial cloud as one way of implementing research that is not being met by the campus. One of the things that, going back to the survey, and this was a survey that came through CAST, the Coalition for Academic Scientific Computation. I am the current chair, but I was part of a working group that did this, and we included responses from institutions that were not one of the almost 100 institutions that are members of CAST. One of the interesting things that we got was that 83% have only on-premises HPC. The other one was that 62% have only on-premises storage. I would say that the disclaimer is that potentially when people were asked about storage, they may have thought about things like Google Drive. As cloud storage, they may have thought about things like Box. So we need to learn to ask specifically what we're asking, as in any survey. But we continue to look at it because it's another tool. We also continue to wait to have the costs go down, which that could potentially happen. But going back to things that both Andrew and Cheryl have said, there's even more to the total cost of ownership. There are things like compliance. There's things like various legal aspects. There's things like, is there network capacity from the campuses to where they need to get? There's things like costs for ingress and egress, but also how these are covered by grants after the end of the grant. So we need to think about that. The other thing regarding the University of Florida, I'll give a shout out to my fabulous colleagues there. They had a very capable, extremely capable, and fairly large team ready to go with this kind of thing. So I won't talk necessarily right now about MSIs, but these are all things we have to think about.
So what do you make of the bill in Congress, which, if passed, would direct NSF to establish a task force focused on developing a public national cloud computing resource for AI? To what extent do you think that can address this growing appetite for access to HPC and compared to commercial offerings?
So when you look at the bill as presented, they actually did cover a lot of the aspects that come with total ownership, but we have to go back again and again to the fact that a lot of the funding for all these peripheral things that both Cheryl and Andrew have mentioned are not coming from federal funding, and they're not even coming from state funding. There's a lot of compliance also that precludes people from sharing federally funded resources with other people who aren't necessarily federally funded or who aren't on the same project. So there's a lot of compliance that will need to be worked through. And there's a lot of questions about finances. You know, if it's an exceed kind of thing where things are paid for completely by the federal government, which they're not paid for completely because institutions are kicking in when they host exceed resources. But were that to be done, they would have to still work through the parts that institutions are still going to need to cover. And that isn't necessarily, I'm in a public university that gets very little funding from the state, and it has been going down. Compliance is going to be an issue. We see that with NIH strides right now. Who owns the business associates agreement, even when you're getting free credits to use something? So the same will have to be with an AI cloud, especially given the sensitivity of data that may be used for those kind of applications. So there's really a huge, bigger picture here. Everything is workable. It just needs to all be addressed to make a solution actually be a real solution.
Andrew or Cheryl, do you have any additional thoughts on this national cloud computing bill?
Yeah, so I haven't actually read the bill in detail, I'll freely admit it, or indeed at all. But I think it depends what is being established. If it is establishing a funding stream to support, to provide funding to the science to use high performance computing, then that's great. If it's funding to develop yet another center that's just providing resources in the same way that all the other centers are providing, or indeed that the public providers exist, cloud providers exist, then I don't think it's really going to tackle the problem because of the reasons that Sharon was just saying about the constraints and the compliance and who can use it and so on. And also, of course, it's not clear that adding yet another center solves the problems that already exist with the plentiful providers that exist. You know, there's the national facilities at TAC, University of Texas. There are systems at universities and so on. There are facilities in the DOE that can be used. There are the public cloud providers. So the facilities exist. It's getting access to those facilities, I think, is the key constraint. So providing funding for researchers to go and spend on HPC that is appropriate to each researcher's individual need is the big challenge to me. And if that comes together as a national cloud computing initiative, great. But I think the buzzword of whether it's called cloud or not is irrelevant. It's that science modeling capability that needs to be funded. And for it to be focused onto a wholly new center, there would need to be something special and different about that center to justify essentially not improving the existing centers that exist or giving the widening access funds to those centers and funding the users rather than the infrastructure. There's a danger when you fund a center, you end up funding infrastructure rather than the science and the users that can make use of that.
Thanks.
Yeah, and I would just say, I mean, the more compute power that's available, the better. I mean, that's definitely going to help, but it's not going to be the only answer. I think it's got to be combined with, there's obviously still a lot of things that have to be worked out from it. And if it is just another center, I don't think that really takes us very far. I think it's got to be used in conjunction with things that are, maybe potentially like the framework that we did with Florida. So I think it's got to be a combination of those things.
Thanks. Cheryl, there's actually recently been some complementary research in this area that shows that even within academia, compute power is concentrated at the more elite universities, with mid to low tier research organizations missing out. What problems does this cause?
So I think several different ones. I think we learned a lot from COVID research. So the HPC consortium that was put together for, to do research around COVID, where it gave access to, anybody that had some potential research that would help in the fight. What we found is there were a lot of people that had some great research and some great science that they were doing that were, from the elite universities, but also not from the elite universities. So as they started to get access, there was a lot that had to happen to get their code optimized to be able to take advantage of these new compute capabilities, and which we were able to do pretty quickly, but still it was, work that had to be done. And, in one case we saw, and again, this was somebody that was not an elite university, but really important work, a 30x increase in the capabilities that, and what they were able to do, as 30x speed up in their work. So unfortunately, then they don't have nonstop access to that system. They had to go back to their university where they were, working, and they were working on a 7 or 8 year old system. So it kind of like takes them back. So we've got to figure out a way, I think, to, be able to keep those capabilities going, or make sure that, again, outside of those elite universities, that they've got ongoing access to the right resources. So it's not just at, those places. The other thing is I think we're really starting to look at, if we only rely on them, there's going to be a vast gap. As we start to look at, again, we're at the very beginnings of AI, even though those of us that spend a lot of time in it, it feels like it's, very ubiquitous. It's still very early. But as we look at, I was on in a meeting with some agriculture. So it was the strawberry farmers and some other folks that are going to be users. They're going to have needs for using AI. Well, the skill sets that that we need to provide as a nation have to come from, there's not going to be enough if they only come from those elite universities. It's got to come from, across our nation. And I think sort of the third part of this is there has been this ongoing brain drain in those elite universities where companies, the large industrial companies are being able to lure away those top researchers, and NVIDIA included in some cases, to come and work in industry. And so, again, even that pool is potentially shrinking. So, I think and I guess the last part of that is one of the top topics is around ethics and bias in AI. And so diversity is going to be really important, and diversity outside of, again, just the elite universities is going to be really important to that work.
Thanks. Sharon, how have you seen the post-COVID change at your own university? Because as Cheryl said, we've seen NVIDIA and these companies joining consortiums to share resources. And over the summer, AMD donated an HPC network at universities across the United States. How are you seeing it at your own university?
So I would say that although I am the one from academia here, I am from one of the top public universities in the country that has the most NSF funding, for example, considered number one in NSF funding and a lot of NIH funding. So I don't, we have our resources. We always need more resources. We've always used double the amount of hours on Exceed than we have on our own local on-prem. But that's a huge luxury to even have half of the number of cycles that were used on Exceed by our researchers on-prem. So the fact is that there are many researchers that are using consortium resources. I think that though we aren't representative of a lot of these smaller institutions. So as these faculty members or other researchers are using off-prem resources, they are still getting support from on-prem expertise, for example. They are still happily and blissfully unaware of the fact that we have great network connectivity to wherever they need to go. You know, these are things you can't take for granted. Some of this has to do, you know, maybe skipping into the MSI kind of way of looking at things, because we do need diversity of institutions. One of the things that I've seen as we talk in CASC about how to increase the diversity of institutions that are involved in CASC, so that more knowledge can be spread, so that we can learn from other people. We're supposed to be advocating to the government about needs. We need to be able to include all these different types of institutions so we can speak for them as well. There's a catch-22 to a lot of this, including for the plans for funding. The catch-22 is a lot of these smaller institutions, and MSIs tend to be smaller, or HBCUs, all these institutions do not have a central institutional commitment to resources. So going back to your question, we do have at my university, so if they're using another tool, if they're using a NASA computer or they're using a consortium computer, they're still getting support. These smaller institutions, you know, who would be their support if there's no central group or central commitment for this kind of thing? And the catch-22 for being part of these organizations many times is that the central group or a large group that represents research computing on campus are the ones that are members and active in the groups. If you are a faculty member, you know, the only computational faculty member at your institution, you can't be part of a group that involves these bigger outfits, right? And centralized and institutionally committed outfits.
I guess one of the things I heard in researching this report, other than having this issue with not having a centralized kind of body, is that companies are saying, we want to partner with HBCUs, we want to partner with MSIs, but we're struggling because when we try, they don't have land, and we don't know where we'll put the actual on-premises system. Have you seen or have you heard those issues, or what do you make of that?
I don't think it's I mean, I'm sure there's a land issue, but there's a land issue for every Ivy that is in a urban area. For example, Harvard. They've resolved their issues, as you mentioned. The Massachusetts Green HPC Center is very far from Harvard, and it's in a rural area, and that's where they keep their compute. So I think going back to what I was saying, the problem is, I'm sure land is a problem in many places, but the problem really is the institutional commitment. Who is your support? Let's say a HPC system lands on your institution, now what? You know, who's maintaining it? Who has the expertise? Who's paying for the power? I mean, you have to, in my line of work, you have to think about everything that's down in the weeds. You know, where are the institutional priorities? Who's going to pay for data storage? All these things are in my way of seeing things a lot more obstacles than just where are we going to put it.
Mm-hmm. Thanks, Andrew. On a kind of similar vein, other than this kind of what will we do with the gap, we don't have enough. Even with what we do have, it's kind of hard to manage resources because, you know, I'm hearing we don't know what to measure. Is it time to completion? Should we be measuring performance, energy, consumption, performance per dollar? What problems have you seen this cause for purchasers?
Yeah, so I think just adding to what Sharon was saying for a second, it's not The other part of it is that central resource is there to tell the researchers and the institution that HPC resources exist for them to get access to. I mean, that's one of the biggest problems is just awareness of what is out there for researchers to know how to go and use stuff that's external to the institution or indeed internal to the institution. You know, I mean, I think even in a high-profile HPC institution such as University of Michigan, I'm sure there are researchers on campus who haven't quite realized there's a central facility they can use yet. If you imagine how much worse that problem is at all of those institutions who don't have a central facility with people telling them that they exist. So for me, the big challenge is awareness, getting people aware that stuff is out there. And then if you kind of think how much science is done with HPC with those few elite institutions or elite researchers have got access to it, just imagine how much more could be achieved if all of those researchers, all of those institutions had access to these capabilities. So that, for me, the broadening access is the big win. If we can, any tiny step along that will deliver huge benefits. In terms of the measurements and metrics and so on, measurements and metrics around HPC are not easy. It really depends upon what you're going to use that metric for. Is it to measure the performance of the HPC center, or is it to measure the performance of the researchers using it, or is it to try and tune the operation of the facility? And so you end up measuring different things depending on which of those you're doing. So, ultimately, at some level, you want to try and measure, the business impact or the science impact or the amount of science delivered by the facility, or the impact of the science delivered by the facility. That's pretty hard to do, but that ultimately is a goal. And so we often end up using proxies for that, such as the number of simulations run, or the number of papers published that hit the front page of Nature or Journal or something like that. They're not great proxies, but there's some level of proxy. It's when we descend down to very system-focused proxies, like the utilization of the system, system utilization metrics. That's when the proxy link to the science delivered from a facility really gets quite weak. And ultimately, it just tells you the system's busy. It doesn't tell you you're doing anything valuable or not. And the example I often use is you measure the value of a telescope by how many stars you discover, not by how long your eye is stuck to the end of the thing. Now, it's not quite separable, because if your eye isn't stuck to the end of the thing long enough, you decrease your probability of finding the stars. But ultimately, it's still that overall, it's the outputs that matter, not the inputs, not keeping the machine busy. You have to have the resources there so that you can do the science, so that you have the chance of creating the impact. And then, of course, you want to try and get the best. Value out of the investment you're putting into that. So that's when you get to some of these other metrics that are closer to cost. So things like performance per dollar, or the energy consumed, or the total cost of ownership, and so on. And that's really about extracting the maximum science out of the investment that's available, rather than necessarily trying to hammer down the price of every single compute hour, because that may end up just increasing the cost of the science if you've then got to find 300 people to tune the code to grab that extra little bit of performance out of it. So that for me is the thing. Try and find ways to measure the science, understand and manage the cost to get the best science out of that thing. And then there are cases where it makes sense to invest in doing something quicker, or in so the example I often use, if you have a system that is doing emergency simulation work, so think of hurricane modeling or wildfire modeling or whatever it is, you need that resource when you need it. It's not as if you can predict, it's not as if you can book it in the diary now, November 1st next year we're going to have to model a hurricane. You need the resource there when it's there, and that means you have to have some agility, some responsiveness in the system. If you're running it consistently at full utilization with a massive queue and so on, and by the time your hurricane modeling gets through the system, it's too late, the whole city's being flattened or whatever. So for some cases, actually carrying a bit of space and agility in the system might look like a cost up front, but if you don't have that, then you won't deliver the value of the reason the capability is there in the first place. And so effectively, you've made your cost infinite for no value. So there's things like that mean it's non-linear relationship between cost and value delivered sometimes.
Thanks. I was smiling throughout that because I was wondering whether we'd get one of your famous analogies, and in this event we did, so glad to see that. We actually have quite a few questions coming in from the audience. Please keep them coming. So I just want to turn to some of these while we can. Cheryl, one of the questions is, what are other countries doing on supercomputing or HPC? So I touched on the EU, but do you have anything to add?
Yeah, so I think there's an enormous amount of activity, particularly in the Asia Pacific areas, particularly China. So I know a couple of years ago, China designated 31, I think it was, AI universities, and they've been investing pretty heavily into those, to both from a skills standpoint and training standpoint, as well as from a research standpoint. I think we're probably, again, EMEA has made the, Europe has made the decision to, for their Euro HPC things. And so they're probably similar to where we are from the United States, but just up north in Canada, they've been very active in continuing to invest in AI. Probably, I don't know if I couldn't really measure it compared to, size wise, but they've made some pretty significant investments from a research standpoint and from a infrastructure standpoint to support AI.
Thanks. Sharon, one of the questions is, with regard to increasing numbers of women in STEM fields, can you elaborate on any efforts at the K through 12 levels? Waiting until post-secondary seems late. When do you think is the best intervention?
So I think the best intervention is all the time. It is very obvious, there's been numbers for STEM, there's numbers that show that, after fifth grade, girls suddenly stop trying to be involved in STEM because they feel that they're judged. There have been numbers that show that the number of girls' scores in math, I believe it was, math tests, are a function of the number of boys sitting around them. I mean, there have been some pretty astounding numbers, but you have to realize that this isn't just fix the incoming and we'll be good. Retention, in my mind, is even bigger a problem, and retention is all along the pipeline, but it's also it goes all the way to senior management. So we have to bear in mind that there are, let's try and keep the diversity we already have is one way of looking at it. Let's make sure that people are comfortable staying in these communities. Let's make sure that they're recognized, even if they're used to being marginalized. Let's all work to make sure that it becomes clear who should be getting credit, that we stop thinking about the prototype of who should be an HPC, and that covers everything from gender to ethnicity to where they come from academically, socioeconomic, all these things. I mean, we need to reflect the whole population. So yes, we need to start doing that very early on. We need to stop, having robotics teams in high schools that have all male, maybe one or two females, and they're doing the marketing. Things like that. We just, if everyone were aware of this, it would be a lot less of a problem all along the way. And it's okay that we all have biases. When we, even women who take the Harvard bias test, find out that we have biases too, right? Even people of color find out that they have biases. It's the society we've grown up in. So we need to work. There is no fast and easy way of solving this. We need to have awareness all the time and to keep on questioning ourselves when we hire people, when we teach people, when we read articles, and notice who's being quoted and who isn't being quoted. When we write articles, who are we looking to quote? Who are we looking to put on panels? All these things are all part of this.
As a quick follow-up, one of the things we talk about in the report is the Blue Waters project at the National Center for Supercomputing Applications that had an applications category specifically open to researchers at US academic institutions who are women. What impact did this have? Is it still ongoing? Are there similar initiatives elsewhere?
So I'm not, is that for me?
That's for you.
I'm not aware of very similar initiatives. it is true that the numbers, and you can read the numbers in the last annual report for Blue Waters, which has changed, as the grant came to its end, it has changed. So the program has to be different. But you can see that there was some success, but the success, it's hard to measure the success versus just going through the usual way of applying for time on Blue Waters. And I think that's what needs to be assessed. My suggestion would be that when we look at this, we try and figure out why would we need something like that. So usually there are two reasons for needing a special program to encourage underrepresented groups. One of them is that when reviews are done, there is some bias involved, and groups are not managing that are underrepresented are not managing to get the same fair review, or they're not being seen, or because people are looking for something specific, they're not being seen as people who should get whatever it is when you're hiring or when you're reviewing proposals. The other side is, are underrepresented groups afraid or not comfortable applying for these things because they think they're not going to succeed or because they think they're not good enough? So this goes back to the work that has to be done. Some of it is very simple. There are fabulous underrepresented PIs, from these groups who went through the regular way of getting allocations, but they aren't, maybe we aren't seeing them enough. When you go to a Blue Water symposium, you see some of these people. But if you're at that symposium, you probably don't need to be convinced because you're already a PI. So showing this ability to show the diversity that is possible makes people more comfortable seeing themselves in this position. I will note that these programs that do have fellowship or fellows, and Blue Waters had one such program, have been very, very, very successful because they can maintain a balance, and they can make it visible that there are women, that there are people of color, and so on. And these in turn into the heavy users afterwards. But it's a slow process.
Cheryl, one other issue in the kind of pipeline that we talk about in the report is the inability for students who are studying computer science at 2-year colleges to seamlessly transfer into 4-year colleges. What other workforce challenges do you think need to be addressed to kind of ensure that we're preparing the future and also the current HPC workforce? I think you might be on mute.
I was doing so well there. I think that one of the things I already mentioned is that, again, we're sort of at the beginning of this and we're seeing AI it's just starting in different industries. So the fact that AI in particular, or high performance computing, is going to be something that's going to be a part of almost every degree program. So having those skills, having the capabilities in each of those different degree areas. A lot of universities have done some great things with AI institutes where they sort of marry up somebody with a computer science background with somebody with a non-computer science background to be able to do research. And I think that's a great start. I really like the way that University of Florida is doing it, in that their plan is that every single, even undergraduate student, will have the ability to have a baseline of understanding from an AI. So as we look at, again, strawberry companies, strawberry growing companies, other places that are going to be using AI to have those skills. The other thing that a gap that I see pretty regularly is that, especially as we look at things like, I'm working with an MBA school right now, is that they typically don't have the size of data as part of the curriculum to be able to look at where accelerated computing really is going to be needed when they get out into the workforce. So they're working with really small, data sets that can be done really quickly on their laptop. And the reality is when you go out to the workforce, it's going to be a different set of skills. So there's going to be this gap, not only in the number of skills or the number of people that have the skills to do the work that's needed, but the kind of work that's needed, even if they do have some of those skills. So I think there's a couple of different areas. But I also, I think it's just the 2-year to 4-year colleges, again, is definitely a big gap. And I know that some of the universities have some great programs that allow them to, that are working directly with them, but I think it's not everywhere.
Andrew, another one of our audience questions is, should there be an added concern with regard to data privacy and protection as the need for HPC research and use expands?
That should have always been a concern, I guess, is the real answer to that. There have always been a number of standards or compliance issues that have applied to research data, especially where it deals with individuals or identifiable individuals, or with health data, for example. And most institutions who have a sizable HPC presence have people who understand those issues and how to deal with the compliance issues. Certainly, the big cloud providers have all got the compliance regimes in place for all of those. And I think, Azure lists something like 90 different compliance regimes we're fulfill and so on. So I think it's a part of modern HPC, but it's always been a part of simulation science to have to worry about these compliances. I think awareness of it is getting better, and I think making it a standard expected part of certainly the public cloud providers, but also institutional HPC systems is becoming more widespread.
Thanks. Sharon, another audience question is, how could we lobby for funding in areas adjacent to AI, like data collection and labeling, given that online data sets favor a privileged minority of the populace?
Yeah, so that's an important question, and what I work closely with the libraries at my institution, and I would always state that libraries are the people who know how to curate data the best, because they've been doing this for a long time. We also have consortiums that are out of the university. One of them is very well known, ICPSR, that this is what they do. However, funding is never channeled by externally for long-term curation and storage. And we've been talking about this with funding agencies forever. And when I say we, I mean my broader community. It's not me explicitly. I think one of the things is to make it, one of the things that the community is slowly doing is, for example, attaching DOIs to data sets, including data sets in your CV, things like that then make things like data sets as important as other artifacts and products of research. The other thing is to really make it very clear that this isn't a 3-year funding that is going to deal with it. We have to think about how we do this. You have to think of the library in Alexandria way of looking at things, and not just, true, you do need active data storage while you're working, but if we're trying to preserve things for others to do research on, if we're trying to think of sharing, if we're trying to think of findability, these things are longer term things. We have to have funding for longer term, and we have to include the right people in it. The people who are the findability people, the people who are thinking about sharing. My institution has recently had a working group that I was part of in response to the AAU and APLU. I can't remember the acronyms for PARD, public access to research data. And we gave a very long report because we tried to cover every little bit that would need of the university that would need to be involved in this kind of thing. And that's just one university. If you expand that to how do you get sharing across the world, there's a lot that goes into it. The devil's in the details, the devil's in the funding, and everything comes down in the end to expertise and money. Thanks. So I wish I could say, just do this and we're good. But there's a lot to think about. But most researchers and universities completely are in agreement that this is something that is extremely important.
Thanks. Cheryl, another question is, from a regulatory compliance perspective, what do you foresee as impending challenges, whether at the federal, state, or international level?
Well, I think we've covered a lot of, are you looking at regulatory compliance from data or from, is there, if there's any more specifics on that?
It's open-ended, so however you want to interpret it, really.
I think there's plenty of challenges. I think things like, as Sharon just mostly talked about, is the data itself. There's a lot of regulatory and compliance as we start to look at things like healthcare data and those sort of things. I think that's probably one of the biggest, security overall, are big issues from that standpoint.
I think we have about 5 minutes left, so I'm just going to take a couple more questions. We have one, Andrew, from Indra Klein. From an IP perspective, do you think that Congress needs to consider changes to legislation in the Constitution with regards to terms of patent protection?
Probably.
Yeah.
Probably. I mean, I think this could explode easily into a very long debate rather than just a short answer. But there are a lot of discussions around. So if the research is fully funded by the taxpayers, then there's a reasonable expectation that the taxpayer gets a benefit and not just essentially giving a gift to a university to then go make a whole load of money from taxpayer money. The reality is that most institutions are putting some of their own intellectual capital into it as well. But then you've got to separate out that some of that intellectual capital is actually already funded by the taxpayer again. So it's not trivially separable where the investment has come from, which is part of the challenge in the first place. And then secondly, it's not just necessarily about doing what appears to be the right thing based on where the input or the actual intellectual capital or investment comes from, and therefore who should own it, but also what's the best thing to do to stimulate the future. So whilst it might be sometimes the best thing to do to make sure that the state or the government or the nation owns the IP, that's not always the best way to drive the exploitation and to deliver the long-term better societal or economic impact. Sometimes actually making it easy for companies to pick up that IP and then do something with it is actually a better way to deliver a longer-term impact to the economy, even though in principle you're giving a company a kickstart from taxpayer funding. So it's there's easily an hour's panel on that topic alone. I don't think there's a short answer to it. So.
Great. So I think if we just, to end this off, if we could do a quick round of what you think is the most important, part of this story that the United States needs to do to increase access to supercomputing. And I will start with you, Sharon.
There's so many. I think for me, my main concern is about diversity of institutions, access for everyone. So sharing, making it possible to share resources would be the most important thing to me. And that includes data sets and expertise and everything else that goes into it.
Thank you. Cheryl?
I think from my perspective, it's the biggest thing that I'm concerned about is that we're trying to build for what we see today. And I don't think that we really, and I know I feel like I beat this dead horse for a while, but I do think that the opportunity for us, if we're not able to capture that now, that we're going to dig ourselves into a hole that will be really hard to get out. So we've got to be thinking, big time growth in this space.
Andrew?
Yeah, so for me, it's the broadening access, and that includes the people side of things. It includes the data curation side of things. It includes just the awareness that those opportunities exist for a number of researchers, and fundamentally involves reducing the friction for researchers from a broader base to get access to the capabilities, and indeed to contribute to the capabilities. It's not just a case of some magic that we have in the elite institutions that we're letting people use. There's a broader base of people who can really contribute to advancing the state of the art in supercomputing as well, and AI as well, that we should help to contribute and deliver that. So I think it's the broadening access that to me is the biggest benefit and also the biggest challenge.
Thanks very much. Thanks to all our panelists. And thanks for this great conversation. You can all find a copy of the report on our website. And if you have any further questions, just feel free to email me. Thanks very much.